Dear ladies and gentlemen, let me welcome you to the EAI International Conference on Intelligent Edge Processing in the IoT Era, held in this virtual interactive setting. I am Elena Davidova and I would like to address all of you on behalf of EAI and Edge-IoT 2020. I would like to use this opportunity to address the organizing committee, the authors and all the participants on behalf of all of us here at EAI. I would like to thank all of you for being a part of this conference and for your involvement with EAI. In particular, I would like to thank the General Chair, Professor Sergio Ivan Lopez, from the Polytechnic Institute of Viana do Castelo, together with the whole organizing committee, for their excellent work during the conference preparation. Today, during this streaming, we would like to invite you to participate in the Q&A sessions. During each video, please write your questions about the current presentation into the chat window. After the presentation is done, the session chair will ask selected questions to the author of the presentation in a live conversation. Lastly, I'd like to use this message to invite you to join us again at the EAI Edge-IoT 2021. Should you be interested in becoming a part of the next year's conference, please do not hesitate to contact us at the email address below. Similarly, if you are interested in discussing other possible cooperation, a conference, a workshop, or a new event altogether, please contact us at this email address as well. Thank you for your attention and enjoy EAI Edge-IoT 2020.
Hi everyone, my name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that will allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, SmartSubmit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work-in-progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what SmartSubmit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Hello everyone. Today I'm going to present to you Technologies for Industrial Internet of Things Guidelines for Edge Computing Adoption in the Industry paper. I would like to thank EAI International Conference on Intelligent Edge Processing in the IoT area for this opportunity. And also, I would like to thank my colleagues from Valley that were authors on this paper as well. Here's our agenda for today. First, I'll provide some introduction of Industry 4.0 and Industrial IoT. Next, I'll talk about the edge computing challenges and explain some suggestions. And later on, I'll talk about edge computing taxonomy and end up with some final considerations. Before I start, I would like to present Vale, which is the company that I work for. Vale is one of the largest mining and metal companies in the globe. Our headquarters is in Brazil, but we as a global company have operation in basically all continents. Aside from mining, which is our core business today, we also work with logistics, energy, and steel. Our operation abroad covers approximately 30 countries that share the same mission: to transform natural resources into prosperity and sustainable development. First, I want to take a moment to talk about some concepts of IoT, starting with its relation with Industry 4.0. The Industry Internet of Things, as the name implies, is the application of IoT in the industry. It's part of the Industry 4.0 concept that is transforming many segments in the enterprises and challenging industry to rethink their production process. The IoT emphasizes the idea of constant digitalization combining the strength of traditional industry with internet and cloud capabilities. Well, and when we talk about IoT applied in the industry, the architecture implementation should be more carefully analyzed. Many IoT solutions have cloud-based application as a central computational infrastructure to store and then process data generated by different resources. The problem with this model is that it assumes the existence of a stable connectivity with low latency and acceptable response time. But for an ever-increasing demand of IoT data, the high volumes and the fast velocity of data generated by the IoT devices can request a massive amount of network bandwidth. And since the cloud is physically distant from the IoT device, sending application requests and waiting for the result to be processed and then sent back from the cloud cannot be the most adequate response, especially when considering sensitive IoT applications that need quick response to operate. So we can see here that cloud computing may not always be the best strategy for industrial applications, and sometimes the computing needs to be performed closer to the source of the data to improve the possible gaps and the point of failures. So having computing resources close to the network helps us deal with some of these challenges, and that's what I'm going to talk about furthermore. One technology that should be adopted by the industry is edge computing. In some situations, it can replace cloud-based applications due to the network dependency and latency. As I mentioned, real-time and near real-time systems need fast response. And what is the edge? The edge concept is basically to move some of the computational load to the network edge, enabling, for example, to process the data next to where the data is being generated. So the sources is the sensors. By keeping some compute and storage at the edge, companies can minimize delays and reduce data bandwidth requirements. It's no longer necessary to move large amount of data back and forth to the regional data center and to the cloud, and this can lower overall cost operations. But today, in the market, we can find several types of devices that can process data. Basically, any device with computational capability can receive data from things, process that, and process that locally. This can lead to many distinct electronics devices with different characteristics, which can produce management issues when maintaining and supporting these devices. So what are the challenges for edge computing? Let's go a little bit deeper into that. From the industry perspective, some key concerns that need to be addressed to enable a sustainable implementation are mentioned here: the management, reliability, and cybersecurity case. Some of the management concerns are shown here. Lack of management can lead to, for example, no visibility and full manage of firmware, operating systems, and application updates that needs to happen on the edge once in a while. Another point could be due to a wide variety of different devices. If we have extensive variety of software used by edge devices, that can complicate software management tasks. So the more diversity we have, the more different types of devices, the more complex it can be to manage that at a large scale. On the reliability point, unlike traditional IoT devices are generally used in harsh environments, exposed to dust, noise, humidity, under wide variety of temperatures, along with that can bring us some concerns that could end up with unpredictable failures. Cybersecurity is another critical point. Edge devices in the IoT context interact with various access technology. It can make edge infrastructure prone to several cybersecurity attacks. So, to mitigate the risk of attacks on the edge devices, specific rules need to be established. There's a, as I mentioned, there's a growth interest in using IoT edge computing technologies in the industry. But one of the biggest challenges is choosing the right technology for adoption. There are several edge computing solutions available today. However, the industry has specific technology features that needs to be considered before choosing the right technology. That's why we propose an edge computing taxonomy that I'll present here. The capabilities of edge devices are all not the same, as I mentioned. They range from event filtering to complex event processing, such as stream analytics. So the first category of edge device that I'll present here is the edge data capture. It works as a data aggregator for many resources and as a single point of store and forwarding. So as you can see here, the sensors are sending data to the edge. The edge is forwarding that data to the upper layers, that is the internet zone. So it's captured the data, it forwards that data to the upper level as it comes to the edge. So all data that's getting to the edge is forwarded. That's the first type of edge that we have here. The second one is the edge data processing. This is a more specialized device that enables the first pass, the first filter of a data. It makes possible to reduce the amount of data that is transmitted. So as you can see here, the sources are the sensors here that are the sources are sending data to the edge. The edge has a computation intelligence here, so it processes some of the data and sends only that processed data to the cloud. So this is the fundamental difference between the edge data capture and in the role that it plays on data lifecycle. So the edge data processes collected data, process that data, and then forwarded the processed data. Those types of devices can sometimes manipulate physical variables, enact in equipment, or trigger alarms. In some situations as well, the edge data processing allows human interaction through a human machine interface, for example, using a screen or a tablet, as illustrated here. It can be also an input for data on this edge. A quick look at the table here, we can see that some features are the same between these two types of devices, such as basic data filtering, storage, and forwarding, basic data processing. But we can also for sure see here that some are different, as for example, I mentioned the computational model and complex data processing that happens on the edge data processing. So after the classification of the devices, it's necessary to establish rules for their adoption. Some rules can be addressed the same way for both taxonomies, and some are specific for each type of device here. So taking a look to the concerns that are previously presented, management, variability, and cybersecurity case. A few examples of how to handle that are mentioned here. For the management, the devices can be integrated into a centralized device management system, bringing some management functionality to that. Through that, for example, we can have remote software and firmware updates. We can collect information about the health of the device. We can know and track its physical location. We can remotely collect and diagnose errors. We can also check information about the version of the device, the model, the manufacturer, and so on. To mitigate the reliability concern, making sure it's capable of handling environment conditions, especially the environment you are going to work with, it's key. It's really a key here. A few things such as making sure it has industrial protection certification for water and dust resistance. Does it incorporate power optimization and deploy techniques such as dynamic voltage scaling, for example. Concerns such as these needs to be carefully analyzed to the reliability concern. On the cybersecurity topic, it should be covered in fundamental for the application of edge computing in the industry. When we talk about cybersecurity, some things should be addressed as well. Topics, for example, covering security principles for data ownership and access, making sure who and how users can access the edge computing device. Its data information is an important point. A few points regarding cybersecurity that needs to also be addressed that I can mention here are concerns with authentication mechanism, encryption mechanism, having strategies regarding decommissioning and registration is really important as well. The device management solution that I suggested on the management concern for the management concerns can assist in some of these cybersecurity requirements. When implementing these devices, the appropriate position in the network infrastructure in the network is also important as well. The architecture design that is going to be needs to be considered this, so we can mitigate some points of attack as well that can happen on the edge device. So positioning the edge on the right network infrastructure is important. By supporting all cybersecurity rules, devices can be less vulnerable in the industry. So let's do a quick brief recap here. So the use of edge computing devices are increasing in the industry operation, and identifying the type of device. It's important to make sure all functions and characteristics of the need that you have is being addressed. That's why we present a taxonomy to help identify what type of device it is. And to be able to adopt this technology in the industry, some minimum rules should be applied and to help mitigate the risks. So these are the main points that I wanted to highlight. And I want to thank everyone for this opportunity to present our paper on this conference. Thank you very much.
Welcome everyone, my name is Anjas. I'm a PhD student at UNC Charlotte from Electrical Engineering Department. Today I would like to talk about my paper, Scalable Approximate Computing Techniques for Latency and Bandwidth Constrained IoT Edge. Here is the summary of my presentation. First, I will give an introduction about IoT machine vision applications, and then I will describe the motivation to use edge computing. Then I will talk about edge vision system that we developed and present the study of network latency variations at the edge. Later I will present the research questions and the video frame quality knobs that we have identified. Afterwards I will show the study of impact of video frame quality knobs on video frame size and inference accuracy. Then I will describe two scalable approximate computing based algorithms we have developed and their implementation and results. Finally, I will conclude my presentation with future research directions. Internet of Things based systems utilize machine vision for a variety of challenging tasks including autonomous driving, pedestrian tracking, public security, and occupational health and safety. Such applications involve computationally intensive processing of streaming videos from cameras operating 24/7. Transferring such large amount of data generated by the cameras to the cloud in real time results in high demand on network bandwidth. Additionally, these vision applications tend to be latency sensitive. That is, in such applications, events need to be responded within tight deadline constraints, preventing the offloading of computation to the cloud. The bandwidth constrained and latency sensitive nature of IoT machine vision applications motivate the use of edge computing paradigm. In the edge computing paradigm, most of the processing of the video streams happen in the vicinity of the cameras or sensors. Figure shows the architecture of a three-tier edge computing model. First tier is IoT devices including smart home appliances, smart health wearable devices and cameras. Second tier edge consists of edge servers with more compute and storage capabilities than IoT devices. And third tier is cloud servers. Due to cost and ease of installation reasons, IoT devices deployed at the edge make use of wireless technologies such as Wi-Fi and Bluetooth as communication medium to transfer large amounts of data in real time. We developed an edge vision system that collects video frames from multiple cameras and executes several machine vision applications for object detection and pedestrian detection. Figure shows the system architecture for machine vision at the IoT edge. The physical model of our edge vision system consists of multiple IoT camera nodes monitoring video scenes from different angles in an area of interest, such as a traffic intersection or parking lot. All the camera nodes send the recorded video frames to an edge server through Wi-Fi. Edge server aggregates video frames from multiple camera nodes and executes several machine vision applications on received video frames. When we initially transmitted video data from camera nodes to the edge server, we observed that the video data in the wireless channel is prone to large variations in the latency due to interference, both from peer video cameras and unrelated external sources. The interference causes the data transfer network latency to exceed real-time response times, and hence the machine vision application set real-time bounds. In order to understand the latency variations in Wi-Fi channel, we conducted some more network latency measurements. We transmitted video frames with different sizes from a camera node to the edge server while keeping all other camera nodes inactive. Figure shows the impact of video frame size on network latency. From these measurements, we note that the network latency shows an approximately linear variation with video frame size. Video frames with reduced size can be potentially transmitted with reduced network latency. This result suggests that for camera nodes at fixed locations, the latency can be tuned by varying the size of the video frame. These observations led us to explore the following research questions. Can we reduce video frame size to satisfy latency and bandwidth demands from vision applications? Second question is, can approximate computing be used to trade off vision application accuracy for video frame size or quality? Approximate computing is based on the idea that in some applications, selective inaccuracies in computation can be tolerated to achieve gains in efficiency. So in our case, can we reduce the video frame size and quality to achieve reduced latency and bandwidth, and if we do that, how will it affect the accuracy of the machine vision algorithm consuming those video frames? Finally, are the developed approximate computing approaches scalable? Hence, we explored multiple video frame quality modification techniques which when applied on video frames reduce the video frame size. We call these techniques as tuning knobs, which are shown in the table. We identified 10 such tuning knobs. For example, knob 1 is color space modifications. Video frames can be converted from one color space to another resulting in total size reduction. We selected 8 such color space modifications, which are grayscale, XYZ, HSV, and so on. Similarly, knob 2 is blurring. Video frames can be blurred by passing them through various low-pass filters. We chose the filter kernel sizes of 5, 8, 10, 15 and 20 as possible knob settings. Some of other knobs include denoising, contrast stretching, Gaussian filtering and 2D filtering of images. All these knobs can have different knob settings as shown in the table. So first we applied these knobs to see if they produce reduced size video frames, and we found that application of all the knobs result in reduced size video frames. Here in this figure, two examples of knobs which are blurring and denoising, and their achieved size reduction are shown. When we increased the filter size of blurring knob to 20, we could achieve a video frame size reduction of 75%. Similarly, when denoising filter size is increased to 30, we could achieve a size reduction of 67%. However, reducing the information content by applying these tuning knobs on video frames could impact the object or event detection inference accuracy of machine vision applications consuming those video frames. In general, the impact is dependent on the particular machine vision application. To evaluate the impact, we chose object detection as the machine vision application. Object detection machine vision application using EfficientNet from Google Brain team. We used a publicly available vision dataset Microsoft Coco consisting of 91 object categories with more than 300k images. We chose mean average precision as the inference accuracy metric for object detection. We first modified the images from Coco dataset by applying tuning knobs and then inputted the images to EfficientNet to calculate the MAP score. For each knob setting applied, we calculated the resulting MAP score accuracy from EfficientNet. Figure shows the resulting MAP values for two knobs blurring and denoising. We can see that when we increase the blurring and denoising filter kernel sizes, the MAP score reduces. Setting 1 of blurring knob could achieve 90.8% of accuracy, and setting 2 of denoising knob could achieve 93.5% accuracy. This figure shows the visual impact of application of tuning knobs, blurring and denoising on object detections. Figure 10 is the unmodified image, whereas figure 11 and 12 are modified images. Both the modified images have few missed detections but preserve most of the true detections such as person and bicycle. In figure 11, by using setting 1 of blurring knob could achieve 58% of size reduction with an accuracy of 90.8%. Similarly, in figure 12, by using setting 2 of denoising knob, we could achieve a size reduction of 50% with an accuracy of 93.5%. These observations indicate that approximate computing can be applied in case of these tuning knobs. Lower quality video frames with smaller size can be transferred with lower network latency and bandwidth if they provide acceptable inference accuracy. The observations indicate that tuning knobs provide a mechanism to send reduced size video frames with acceptable inference accuracy. It should be noted that the network determines the size of the video frame that needs to be transmitted, while the machine vision application decides the inference accuracy bounds. To select the knob settings that constitute the targeted frame size and target inference accuracy, all combinations of settings of identified knobs need to be characterized. However, combining the knob settings for different tuning knobs results in a combinatorial explosion of the design space as seen in this equation. For tuning knobs from 1 to n, this number can be represented using k total, where k total is the number of knob combinations and ki is the number of knob settings for the ith knob. For the 10 tuning knobs identified, this will result in a total knob combinations of 22 million. Computing and storing 22 million combinations is prohibitively expensive. Therefore, we explore two scalable algorithms to solve the combinatorial explosion problem: the design space pruning heuristic algorithm and machine learning based algorithm. In the pruning heuristic algorithm, a knob search space with n tuning knobs consists of n steps in the algorithm. In the first step, of this algorithm, we change the knob setting for a single tuning knob while keeping settings of other knobs at their default and calculate the frame size and inference accuracy metric. We repeat this process for all knob settings independently for each knob. We then filter out knob settings that result in a lower performance on the inference accuracy metric, meaning knobs with accuracy lower than an application specified threshold are discarded. This completes the first step of the algorithm. In the second step, we chose pairs of knob combinations from distinct knob combinations obtained from first step. A filtering step similar to first step is then applied to filter out knob combination with lower performance on the inference metric. This completes the second step of the algorithm. The process is repeated next considering 3 distinct knob combinations from the knob settings obtained from step 2. The algorithm terminates when all n distinct knob combinations are considered in the nth step. Each step prunes the design space by eliminating low-performing knob combinations. In contrast to pruning the entire knob space to identify useful knobs, a machine learning algorithmic approach can be used to predict video frame size and inference accuracy. To build the model, we first collect the input data required to train the model. We sample a small subset of knob combinations from the total possible set of knob combinations and evaluate the video frame size and inference accuracy for sampled knob combinations. We then transform the collected data to a data set consisting of knobs, video frame size, and accuracy values. We split the data set into train and test sets and developed 2 machine learning models to predict frame size and inference accuracy. To build the model, we explored a recently proposed model called CatBoost Regressor from open source gradient boosting library CatBoost because of the categorical nature of the input features, which are knob combinations in our case. Hence, we built 2 machine learning models, one to predict video frame size and second one to predict inference accuracy. Now we move on to the evaluation of the scalable approximate computing algorithms. A set of 146 knob combinations were identified using the pruning heuristic algorithm from the 22 million knob search space. To identify these knob combinations, we set the inference accuracy threshold of the efficient det object detector to be greater than 80% of the MAP of the unmodified video frames. The application of all 146 knob combinations of knobs identified above results in different sizes of video frames all lower than the original. Figure shows the plot of the normalized MAP expressed as a percentage versus video frame size for video frames with COCO dataset modified using the filtered knob combinations. The video frame size buckets in figure correspond to different combinations of the knob settings with different resulting MAP. A higher MAP indicates a higher inference accuracy for efficient det. Using the pruning heuristic algorithm, we could identify knob settings that achieved 71% video frame size reduction with MAP score of as much as 82% of the baseline MAP. This key observation enables the transmission of smaller sized images with less MAP but with reduced latency and bandwidth from the IoT camera nodes to the edge server. To evaluate the machine learning algorithm, we sampled 1000 knob combinations from the knob sample space to generate the input data for the model. Next, the sampled knob combinations video frame size and inference accuracy are calculated. We fed the samples to the developed CatBoost regression models and predicted frame sizes and MAP scores for the knob combinations. Figures show the percentage variation of actual and predicted MAP and video frame size with respect to percentage of knob combinations in the test set. Video frame size histogram shows that 78% of the knob combinations fall within 10% of the video frame size error. The MAP histogram shows that 82% of knob combinations fall within 3% of MAP error. Since we could predict accurately most of the knob combinations, video frame size and inference accuracy with less than 10% error, using the constructed models, we conclude that the models are sufficiently accurate. Comparing the 2 scalable approximate computing algorithms, the categorical boost machine learning model-based algorithm achieves comparable accuracies to the pruning heuristic algorithm. The machine learning approach is more scalable, both in terms of the number of knobs and the number of settings for each knob, since it only has a one-time training cost. We now describe the applicability of these algorithms in an IoT Edge Vision system. Consider the IoT Edge Vision system described previously, consisting of multiple cameras and an edge server deployed in a public space such as a traffic intersection for detecting pedestrians. The pedestrian detection machine vision application running at the edge server informs the real-time latency and accuracy bounds for the video streams that need to be sent from the IoT camera nodes. So, a latency controller as shown in this figure can be operated at the camera node. Notice that the controller consists of a lookup table that stores knob combinations, resulting video frame size, and the inference accuracy. First, using the latency bounds, the controller calculates the video frame size. Then it searches the lookup table to find the knob combination that satisfies this video frame size and also the target inference accuracy. And the lookup table can be constructed using any of the approximate computing algorithms described previously. In this paper, we are now moving on to the conclusion of this presentation. In this paper, we explored the problem of latency and bandwidth constrained operation at the IoT edge for machine vision applications through the technique of approximate computing. We identified a number of video frame transformation techniques that can result in reduced frame size and effectively act as latency or bandwidth tuning knobs for the application. Since the design space suffers from a combinatorial explosion problem precluding exhaustive characterization of knob combinations, we investigated scalable algorithms to facilitate our approximate computing approach. We experimentally evaluated two approaches, a heuristic-based tuning algorithm of the design space and a categorical boost machine learning model-based algorithm, and found that the machine learning model-based algorithm is more scalable and flexible. Among the future work directions, we could incorporate the approximate computing-based algorithms proposed in this paper in latency and bandwidth constrained edge and cloud computing systems. We have targeted object detection in this work since it is a basic kernel in many of the machine vision tasks. We could also explore the use of the proposed techniques on other machine vision tasks such as object tracking, image segmentation, and activity detection. With that, I would like to conclude my presentation. Thank you.
Hi, my name is Jorge Coelho, and I'm here to present our work titled Collaborative Task Processing with Internet of Things Clusters. This work was done in collaboration with my colleague Luis Nogueira. So the motivation behind this work is that we are seeing a huge increase in IoT devices. So they are everywhere now. There are some forecasts say that by 2025 there will be around 75 billion of these devices. Well, these devices have some computational power, and we want to know if it is possible to use these devices like in a cluster for computation that is not their main functionality, is not their original functionality. We want to use their spare power. This will allow also that computation sometimes does not need to go to the cloud to be processed, so we don't need to send data to the cloud to have it processed and then send it back. We know that we will have IoT devices everywhere. We know they are connected, but how can we explore their spare capacity and how to organize them in a cluster and make them collaborate? Well, we try to answer those questions. What seems to be not natural is to use computational flooding. We just send a task to the device, it executes and returns the result of the execution. How can we do this? This is not easy. The devices are not prepared for this kind of operation. I cannot buy like a smart lock and try to communicate with it in order to get it to execute some instructions. That's not easy. Probably manufacturers are not interested in offering such type of interface to their devices. Clearly, it's not easy to use any of these devices with a purpose which is not the original one for which they were built. Anyway, they have some computational power, and it's a pity that it's not used. So the first thing we realize is that we need to rely on IoT devices which are open devices. And we decided to use these devices which are single board computers and which are open. They are becoming increasingly popular due to their enormous applications. They can be used for many things. One of the most famous one is the Raspberry Pi. So it has these connectivity features we need with several cores. It has up to 8 GB of RAM. It's like a full-fledged small computer. It runs Linux, which is a friendly system when we want to do some of the things we want to do. We have these devices like for a given functionality, for a given purpose, and we want to use their spare capacity. Well, Linux is a system, an operating system where the kernel is prepared to implement resource reservation. So I can easily tell to the system that these resources in terms of memory and CPU, they cannot be touched. They are reserved for the main purpose of this device. But all the remaining resource I can use for me, and this is a very useful approach. So we can use the spare capacity of these devices without interfering with their main functionality, and it has many applications. Our idea is to use the computational offloading approach, but for open devices like the Raspberry Pi, and we want to build a framework that coordinates all the communication and task offloading. So conceptually, the framework is like the image I have here. We have a problem, so then we can do some data decomposition of that problem. We can assign parts of that problem to different nodes or IoT devices, and then request them to execute some operations over that data and return the result. That's our idea. So now we have a set of open devices, the idea of exploring them as a cluster, okay? But how do we know the amount of data that should be distributed to each of the devices? No? They are different from each other. They are not equal devices in terms of capacity in CPU, in memory, etc. And in which language we should implement the framework? And how do we communicate with them? How do we manage failure? This, of course, is related to the option of the language. How do we know the amount of data that should be distributed to each of the devices? We need to evaluate each of the nodes' capacity. Here, node and device appears with the same meaning. The first idea we had was to use benchmark. And this is clearly the best approach to know or to estimate the performance of a device, but it's also very heavy. And in our scenario, we are dealing with devices that can, at one moment they are available for us, and the next moment they are not available because they were turned off. So we felt that benchmark was not what we need, and so we decided to use an estimate on performance, which is clearly not as good as benchmark, but give us an idea of the differences between each of the devices. We use this formula. This is the performance index we defined. And we use the CPU speed in gigahertz, the number of cores of the CPU, the remaining CPU, the remaining RAM, and the remaining battery in case the device has a battery. Of course, Raspberry Pis are not usually used with a battery, but in case the device has a battery, this is important. This alpha, beta, and theta, they are all application-dependent values. It's in the programmer's hands to define these values. We feel that in different applications, they must have different values to make more important the CPU or the memory or the battery. It depends a lot on what we are implementing. This is just a simple example on how I can obtain this performance index value for a device. When we have several devices, several nodes which are described in this table, we may have several performance index values. And we know now how to organize them. We know that the more powerful one should have the more percentage of work. For example, for decomposing the sum of 100,000 numbers, we can have this distribution. So we have this performance index for these devices, and the percentage of power of each device is directly related with the assigned partition for the solution of this problem. That's not always that simple. Many problems don't have an even distribution of work, so things get harder in some intervals. For example, one simple example of this is like computing prime numbers. Okay, this device only has 12% of the partition, but maybe the harder work is there, and so all the coalition, all the cluster will not work, will not be optimized. So we implemented this in asset problem decomposition. We split data in a set of a given number of partitions, and then inside those partitions I have the devices consuming each part of this partition accordingly to their computational power. Of course, here device 1.1 is less powerful than device 1.3. We do this for all the intervals. This has a drawback. It increases a lot the overhead in messages. It's closer to a ticket delivery system, but it maintains the distribution of work in proportion to the performance of the index of the devices. So we felt that this, not being the perfect solution, improves the solution of problems. Implementation. We decided to use Erlang language. So why? It's easy to install it in Raspberry Pi. Functional programming approach is the best approach when you are dealing with multi-core or distributed systems because of not having or minimizing side effects, and it's easy to split the code and execute it in parallel. It has wonderful built-in communication features. It has strong built-in code distribution features, and it's fault-tolerant oriented. This is the perfect language for our purpose. The nodes, the Raspberry Pis, can be master nodes or slave nodes. This is the code for the master, so it initializes the cluster, then it sends the code that should be compiled in each of the nodes of the cluster. It distributes the work to the nodes and waits for the results of the execution, and if needed reschedules some parts of the work if some of the nodes fail to return the result or fail during execution due to some power failure or other. The slave that is executing the code only has this very simple function, which is like wait for a message where it says, okay, execute this code, and it will execute the code and return the result. The Erlang language has a built-in feature which is links. I can build a link between two processes. And if one of these processes fails, terminates, the other process knows that because it receives a message. And this is very useful. So if I have one of my nodes failing, immediately the master knows that that node failed, and it can redistribute to reschedule the execution of the work that was scheduled for that specific node in another nodes which are still alive. How did we evaluate our work? Well, we used a small set of Raspberry Pis and made a lot of experience with them. We have these 4 devices, a Raspberry Pi 3B Plus, 2 of these devices, the N1 and N3, and 2 Raspberry Pi Zero wireless devices, the N2 and N4. They are different because they have significantly different CPUs, with being the 3B Plus being much more powerful, and the 3B Plus also has the double of the RAM that is available in the 0. Let's just show how the evaluation went with one example. We want to find the prime numbers in the interval 0 to 50,000. There's a total of 5,133 primes in this interval. They are not evenly distributed, and the higher ones are more difficult to find than lower ones. Since the problem is not easy to break in balanced partitions, we use that approach I presented before, the enhanced problem decomposition, and we tried with 1 partition, 5 partitions, 10 partitions, and 20 partitions. I may recall that each of these partitions is then split by each of the nodes proportionally to their performance index. Here we choose the node N1 to be the master, but we could have chosen any of them, or even an external computer that communicates with them. With one device, which is the Raspberry Pi 3B Plus, the N1, we need an average of 26 seconds to complete the execution of that code. But if I add the Raspberry Pi 0, I have an increase in performance. So I have 24 seconds now for the solution with 1 partition, but if I have 5 partitions splitting the work, I need only 16.67 seconds. The others with 10 and 20 partitions, they do not show any increase in performance. On the opposite, they are worse than the 5 partition option. If we add another device, then we have 14.84 seconds for 1 partition. Recall, 1 partition here means that this partition is split by the 3. Okay, when I have 5 partitions, I have 5 partitions, each of them split by the 3. And with 5 partitions again, I have 11.95 seconds, which is a good number. I don't have much better results with 10 and 20 partitions. If I add another Raspberry Pi 0, I have now 4 devices. I have 40.05 seconds for 1 partition and 9.72 seconds for 5 partitions. Finally, if I look at this like the performance gain I have by adding devices, I can look at this graph. I have a performance of 33% increase with 1 device added, 55% with 2 devices, and 64% with 3 devices. Of course, they are different devices with different capabilities, so this can vary a lot. We also experimented with the failure in nodes and rescheduling, and this is highly dependent on the capacity of the nodes that are failing. So if they are weak nodes, the failure is not that relevant. If they are nodes which are very strong in the cluster, which have a lot of computational power, we gave them a lot of work to be done, and now they fail. We need to reschedule all this work, and this of course has an impact, and the performance reduces a lot. For example, in our case, failing node N4 has a considerably higher impact than failing node N2, and this is of course due to the different capacity and the amount of work that was distributed to them, as I explained. In conclusion, we believe that it's possible to use the spare computational power of IoT devices, but we need open devices to do that. So thank you very much for listening to this presentation. My name is Jorge Coelho. That's my email. This work was done in collaboration with my colleague Luis Nogueira. That's his email. And if you have any questions, any doubts, you can use our email. Thank you very much.
Hello everyone, I am Sheikh Rafsan Reza. I am a PhD candidate at Prairie View A&M University. Today I will be presenting the paper Inference Performance Comparison of Convolutional Neural Networks on Edge Devices. Now, with the widespread of Internet of Things, large amount of data are generated at edge devices. Now, in order to protect the privacy and security of the big edge data, as well as to reduce the communication cost, it is desirable to process the data locally at the edge devices. In this study, the inference performance of several popular pre-trained convolutional neural networks are presented on 3 different edge computing devices. For our model, we chose MobileNet V1, MobileNet V2, and Inception V3. And for our devices, we chose 2 NVIDIA devices, which is the Jetson TX2, the Jetson Nano, and Google HTPU, and we do the image classification task. Now, furthermore, various compression techniques such as pruning, quantization, binarized neural network, tensor decompositions can be used to reduce the complexity of the model, which can help to execute the model on edge devices. The results of our experiment will provide a guidance for practitioners when deploying deep learning models on resource-constrained edge devices for near real-time and on-site learning. Now, the Internet of Things has become popular with the rapid development of small, local sensors, wireless communication technologies, and new internet techniques. It is generating a huge amount of data which needs to be processed. Now, recent breakthrough of deep learning has fueled a growing demand for intelligent edge device featuring near real-time and on-site learning rather than executing them in a crowd or a strong computing resource. In addition, there are some security and privacy concerns when transmitting raw data to cloud that may contain private information. That's why mobile edge computing has been proposed to bring the computing closer to the data. If we look at the figure, we can see that the IoT devices are used to generate a lot of data. Then these data are transmitted to the cloud, where they are processed and created a AI application. Then the application is executed. Now the current research, our research is to execute the model, to make the model suitable for edge device. For this, it requires to be less complex because of the less resources of the edge devices. Now we use convolutional neural networks for our image classification task. We use 3 popular models, which is the MobileNet V1, MobileNet V2, and Inception V3 for the comparison. The Inception V3, it uses approaches such as factorizing convolution, auxiliary classifier, grid size reduction to build more robust and lighter model. For example, a large 5x5 filter is replaced by 2 3x3 filters. Now the parameter is reduced from 25 to 18. Moreover, 3x3 filter is replaced by 3x1 and 1x3 filters, and therefore the number of parameter is also reduced from 9 to 6. So this helps the model to reduce the parameter, to reduce the complexity. It helps the model to run on edge devices. MobileNet is also most popular for resource constrained devices for mobile and embedded vision computer vision tasks. The aim was to achieve high accuracy with low computational cost. The main idea was to change the standard convolutional into depth-wide convolution and 1x1 point-wise convolution. MobileNet V2 is another version of the MobileNet and more improved version. The difference, one difference is MobileNet version 1. Version 2 has a new layer which is called the 1x1 projection layer. These are the edge devices we used for our experiment. The left is the NVIDIA Jetson TX2, and on the right, the top one is the NVIDIA Jetson Nano, and on the bottom is the Google HTPU Coral USB accelerator. Now, in order to run the Google HTPU, we need a host computer to run. It only does the inference, only speeds the inference. Now, the software tools we use TensorFlow for the basic library. For the Jetson devices, we use TensorRT, which is a software development kit built on CUDA for high performance deep learning inference. And lastly, we use like HDPU, which is a compatible file derived from TensorFlow Lite, which is like a lighter version of TensorFlow. If you look at the figure, TensorRT workflow, we used to like compute all our 16-bit operations. So the figure shows how the 16-bit operation is optimized. First, we use a trained model, and then we use TensorRT optimizer to get the TensorRT optimized graph, and then this TensorRT optimized graph is used to run the inference. For the TPU, it requires a special type of training which is called the quantization aware training. Then we have the TensorFlow model, and then the TensorFlow model is converted into the TensorFlow Lite model, and then it is made compatible for the HTPU. So we use it to run our 8-bit operations. Now for the experiment, we use like ImageNet 2012 validation dataset, which consists of 50,000 images and 1,000 classes. Now for our evaluation metrics, we use like FP to denote the floating point operation, which is like 32-bit, 16-bit, and 8-bit. We compute the 32-bit and 16-bit on the Gerson devices and the 8-bit on the HTPU. We use like many evaluation metrics such as accuracy, memory consumption, pre-trained model running time, average inference time of a single image, also like how many frames per second the model can execute on the device, and many more. We can see the result and analysis on this slide. So if you look at the table, this represents the experimental results of MobileNet V1. The first column is the device. The second column denotes the bit point operation we used. The third column is the accuracy of the model. Then the fourth column is the memory occupied by the model on the device. The fifth column, load, denotes how much time it takes to load the model, load the Python model. And then the time, it basically shows how much time, total time is needed for the device to execute all the 50,000 images. And then we have a average inference time of a single image. And then we have the frame per second, like how many frames can the model execute on a single image. On a single second, with considering only the inference. And lastly, the frame per second denotes how many frames it can do while considering the model loading and image preprocessing also. Now, if you look closer, we can see that the average inference time of a single image, the 16-bit operation is faster than the 32-bit operation. This is as we expected, because if we lowered the bit size operation, then we're hoping to expect it faster. For the 32-bit operation, we used our Keras model, and this Keras model is like optimized using the TensorRT. Now, if you look at one thing, the execution time is significantly more in Nano than the TX2, because the TX2 it has like more memory. Also, the TPU it performs best because it doesn't have any memory; it only accelerates the model. Now we have the MobileNet V2. If you look at the table, we can see that the memory consumption is more for the 16-bit operation than the 32-bit. It is probably because in the 32-bit operation we use like Keras application, which is like a more optimized, relatively new, like the TensorRT process. So the new TensorRT probably takes like a lot more time to load the memory. So that's why we saw that the model loading for the 16-bit operation was quite higher than the 32-bit operations for every case. If you consider the inference time and the frame per second execution, it was better in the 16-bit operation and in the TX2. This is as we expected, because we expected to get like good results than the 32-bit, and the 16-bit is faster, and because of the TX having more memory and more computation power, it performs better. Also, like the TPU is the fastest because the TPU is like more advanced than like optimizing the graph, but it has like more like limitations than the other two models. Now we have our last model, the Inception V3. If you look at the model, we can see that the accuracy is much more better than the Inception model, because the Inception model is more robust than the MobileNet V1 and V2. That's why we found like around like a 0.68 accuracy for the MobileNet models, which is like almost like but the Inception, it performs way more better, having an accuracy around like 0.76 and 0.77. Also, in some extent, it like takes more memory and more loading time too. Also, the most important thing was that it because of it's a more robust and strong model, it takes like a huge time to execute. That's why the average inference time is higher and the frame per second execution is lower than the MobileNet models. Now, the inference time of a 16-bit operation is faster than the 32-bit operation as expected. The speed of running Inception V3 model on HTPU is consistent with the MobileNet V1 and V2 models running on those edge devices. Now, lastly, we can say that this paper, it presents a comprehensive comparison of the inference performance of several popular pre-day and convolutional neural networks on 3 edge computing devices. Experimental results indicate that the HTPU outperforms the NVIDIA Jetson TX2 and Jetson Nano in most experiments with faster inference speed and more accurate results. However, the limitation of the HTPU is that it cannot work independently because it needs a host computer to complete the task. In addition, the TX2 is better than Nano in most cases and most of the evaluation results, because the TX2 having more memory and more like computation power than the Nano. It is also observed that the MobileNet V1 or V2 are the candidate models for speed, while Inception V3 would be more for accurate, which is another example of the trade-off between the inference time and the prediction accuracy. Now, if I summarize the whole paper in once, our goal was to show how the edge devices can be used in different circumstances, because edge devices, they are getting more and more popular, because in some situation it is not feasible to transmit the data. The data needs to be executed at the edge model. So our work can be used as a benchmark to see which model to use in which circumstances. If I say, for example, if I want to use a more robust model and on a with less time, we can select Inception V3 model, because it has higher accuracy than the others, and then we can use the HTPU for faster execution. But the HTPU, it needs the host computers. If the HTPU is not available, then we can use the NVIDIA Jetson TX2. And if we have limited resources, then we can use the NVIDIA Jetson Nano, because the Nano, it has a smaller memory. So we hope this work will help as a benchmark for all the research, for all the edge computing research, and help them to and for acknowledgement, this research work is supported by the US Office of Undersecretary of Defense of Research and Engineering. Thank you for your time. Thank you so much.
Hello, my name is Haris Isakovic, and I will be presenting an energy sustainable CPS IoT ecosystem. There is power in numbers, and this is especially true if we are talking about Internet of Things. In IoT, we collect, transfer, and store data on a massive scale. It allows us to reach further into physical environment as ever before. The projections show that we are going to reach over 100 billion IoT devices by 2025. This number of devices will generate astronomical amounts of data that need to be processed and analyzed. But with these big numbers in play, also questions arise. Is this new revolution sustainable? And how big energy consumption overhead we are introducing actually? To estimate probable energy consumption for IoT devices, we propose a energy consumption model based on a consumer electronics model presented by Andre and Edler. It provides an energy consumption for a number of IoT devices using their average consumption per device in an active and passive state of operation. Also, a ratio between passive and active operation mode, a device operation time over a year, number of IoT devices, a projected energy efficiency increase over the projection period. In this table, we show 3 arbitrary cases calculated using the model, 2 marginal cases, best and worst, and an average case. The average consumption of IoT devices in this case was based on a energy consumption of Raspberry Pi devices. The best case has only 1% of active to passive operation ratio. That means that is active 1% of the time only, and the maximum energy efficiency increase of 5%. In the worst case, we assume that device is fully operational 100% of the time, and the energy efficiency increase is only 1%. And in the average case, we assume that the active-passive ratio is 30% with 4% energy efficiency increase. The projected energy consumption ranges in these cases 500 terawatt hours until to 3,125 terawatt hours. It is worth to mention that we assumed 100 billion devices and the period of 10 years until 2030, and this is relatively pessimistic because the projection was that 100 billion devices is going to be achieved even by 2025. To put this further into perspective, we will project the worst case onto a net electricity generation chart from EU from the year 1990 to 2070. And we can see how big of an impact this energy consumption overhead will make on a global scale actually. IoT systems are structured in 3 scopes of operation: sensor or actuator, fog or edge, and cloud. Sensor and actuator provide us interface with physical environment, either to measure it or to manipulate it. Fog and edge devices provide us the ability to perform certain tasks such as real-time control, data processing, and aggregation. And the cloud provides us with the ability to store, compute, process a large amounts of data in a short time. This increases our ability to process large amounts of data, find insights, and optimize our systems. The IoT systems serve as an infrastructure for process optimization in areas of civil, industrial, or consumer domains. The question is how and what we need to do to make these systems sustainable. What are the steps necessary to create sustainable CPS IoT ecosystem? The first step would be standardization of development methods and model-based design. This would allow us to generate code for IoT applications from standardized libraries, from models, and thus decreasing the amount of errors that would be achieved by bad coding practices or some legacy software and so on. Further, and we showed this in our previous work, the IoT devices could be designed in a way that we have a generic device that can be molded to a specific application with a slight modification to software or hardware. And this is necessary to avoid the additional overhead on unnecessary components within the device. This would reduce the energy consumption. This would also simplify the overall operation of the device. And finally, the energy harvesting. Although it's nothing new, it's being used for IoT over the years and also in embedded devices. The energy harvesting, on the other hand, will provide these devices with free and clean energy that would reduce overall consumption, create grid independence, and reduce chemical pollution with less batteries and less other components that could cause this pollution. And energy harvesting can be achieved using different methods. In this case, for example, using relative motion, we can create a piezoelectric effect, electromagnetic effect, or electrostatic effect. Temperature gradient would create a thermoelectric effect, producing energy with light, solar, and photovoltaic cells will produce energy. We could extract energy from electromagnetic radiation, from ambient radiation, and even for certain chemical reactions. In this paper, we propose an energy harvesting node based on a thermoelectric generator. It uses a STM32 microcontroller interfaced with two sensors, temperature sensor and a global positioning system GPS sensor. It has a narrow band radio receiver to communicate with the rest of the network. The thermoelectric generator is interfaced with the board itself over power management unit that uses the event detection circuit to detect the upcoming event from the thermoelectric generator and to regulate the output coming from the thermoelectric generator. The thermoelectric generator alone is not able to produce stable voltage necessary for the microcontroller to operate. So we are using here the power management unit to regulate and store energy for stable and uninterrupted completion of these measurement and transmission tasks. The temperature gradient required to achieve this is about 50 degrees Celsius for this type of circuit. For this, we require about 2 volts as a threshold voltage, and subsequently the power management unit would supply the microcontroller with a stable 3.6 voltage. So in this chart we see all the stages of operation and the necessary times to do this, and also the currents that are required to perform this. And this gives us ability to scale the required energy to do this. And in our initial test, the TEG showed viable as an energy source for this circuit. The energy consumption of this device can be even further reduced by introducing dedicated circuits, as we used here In this case, we used all the circuits from off the shelf, and only the event detection circuit was dedicated. And also there are thermoelectric generators with higher yield that could be applied, and this would increase a highly potent sensor device. The energy harvesting sensor node based on thermoelectric generator is designed to detect events like wildfires in remote and inaccessible locations. The wildfires are happening all over the world, and they are highly unpredictable, and in some cases very hard to detect. So in year 2018, over 180 people died just in Greece and US from wildfires. The billions of dollars or euros in economic damages for residential, agricultural, and forest resources. Enormous damages to wildlife and the environment in general. And there is also evidence that these wildfires created long-term consequences to the global climate. They are early detection systems that use satellite or camera imaging to detect these fires. However, they operate at certain granularity. By adding these sensors onto the ground, we would be able to protect and target specific areas and detect them very fast, because the short time required for the sensor to be activated and communicated over the narrowband towards the server and then activate the alerts. These sensor nodes are designed to augment the existing, not replace them, but augment existing early detection systems. And in combination with those, they would increase efficiency and timeliness of the early detection systems. The top prototype was built to harvest temperature gradient between the soil and the air temperature. So the one part of the sensor node would be in the ground, inserted into the ground, and the rest would be up in the air. So the sensor node itself, the electronic components, would be on the other side facing the ground, so they would be protected and isolated from the fire itself, so they could actually withstand this temperature change, the rapid temperature change. The device itself requires no batteries, so this is a non-invasive device environmentally, only supercapacitor that would charge it, that would charge relatively fast and discharge towards the microcontroller, releasing energy. The devices can stay dormant for long periods of time. This is their ability to wait for this event to happen can be really long. And this picture shows how this prototype looks at the moment. We are still performing certain heat tests and trying to find loopholes in the design. The device is using narrowband communication, and it has a relatively large coverage area, and networks such as Sigfox could be used to detect these events in an area of 10 to 15, 20 kilometers. The design of the circuit and sensor board itself can be adapted to other energy harvesting devices, such as piezoelectric generators or solar powered devices. This allows us to use this device in other use cases, such as the avalanche detection or flood detection or even tsunami detection. So, as I mentioned before, by introducing these sensors into the existing ecosystem of early warning or early detection systems, we would increase their timeliness, we would increase the precision, and we would be able of targeted protection of certain areas. In conclusion, I would like to go over the topics we discussed here. So the first was an energy consumption model for IoT devices. We showed how big of an impact can the energy consumption of IoT devices in future create on the current energy ecosystem. We showed also how we actually conceptualize a CPS IoT ecosystem in three scopes of operation, and what are the necessary steps to create these systems more efficient. Also, it is worth to mention that in our model we didn't count the overhead required for the cloud computing. So this is a separate model. In the paper we discussed it, and it would add additional overhead to the numbers we propose here. We showed how an energy harvesting sensor based on the thermoelectric generators can be used to detect wildfire. We also demonstrated that it can be really used as a low-cost detection mechanism that would augment and increase efficiency of the current early warning systems, and its ability to adapt to other types of applications such as flood detection or avalanche detection by changing the design from thermoelectric generator to a piezoelectric generator in this case. Thank you for your attention. If there are any questions, please let me know. Thank you.
Hi, my name is Antonio Abreu, and I am here to present the article Low-Cost LoRa-based IoT Edge Device for Indoor Air Quality Management in Schools. Throughout the presentation, I will talk about the motivation and state of the art of the article. The overall system architecture will also be presented, as well as device in the hardware and software component. Finally, it will be possible to observe some data obtained. So we start with motivation. I think it is common knowledge that humans spend most of our time in closed space, including children and adolescents who spend 65% to 90% of their days in this type of space. And one of the great reasons that motivates us to carry out this work is the fact that air quality is essential for a better performance of students and teachers in the classroom. If the limits of indoor air quality are respected, it is possible to obtain more comfort, productivity, among others. Here we can see some of the pollutants found in the classroom, such as carbon dioxide, radon, particles, 1, 2.5, and 10, volatile organic compounds, temperature, humidity, and others. Taking into account the legal limits in Portugal, total volatile organic compounds should not exceed 600 micrograms per cubic meter. PM 2.5 and 10 should not exceed 25 and 50 micrograms per cubic meter. And finally, carbon dioxide equivalent 1250 particle per million. State of the art. The authors developed an air quality study in nurseries whose objective was to evaluate the concentrations of particulate material, 1, 2.5, 10, and total particulate material. With the study, they realized that there was an increase in PM concentrations in the late afternoon due to the cleaning performed by the employees. Thus, they concluded that the ideal was to do the cleaning after the children went home. They also found that the concentration levels of particulate material 1 are higher when the spaces are empty, and particulate material 2.5 and 10 when there is occupation in the room. They found that concentrations were much higher in the occupation period than in the non-occupation periods. In this article, the authors try to understand the appearance of respiratory pathologies, taking into account the quality of the air. For this, they measure the relative humidity, carbon dioxide, and volatile organic compounds in 9 public schools. The results obtained were if the amount of carbon dioxide exceeded 2,100 particles per million, it could have wheezing during exercise and cog at night. If there were large levels of volatile organic compounds, there was a risk of having asthma once in their lifetime, and the symptoms of wheezing and nocturnal cog remain. And finally, system for monitoring and indoor air quality control of the interior in office of school buildings, where main objective was to realize the feasibility of the same way of improving air quality. And system was tested in 3 different spaces, and 4 tests were carried out with approximately 8 hours each, with different ventilation conditions. The system was able to evaluate how to track carbon dioxide and carbon monoxide relative humidity and temperature, and the studied areas were not ventilated, and since the interior space had different ventilation conditions, the authors managed to realize that there is no great difference between ventilation by insufflation and extraction. Whatever the insufflation method was more effective. The following requirements were defined for the project. Is design a low-cost IoT edge device for indoor air quality monitoring in the classroom, compatible with the RN Monitor platform, LoRa technology, powered by electrical network parameters, and the parameters to monitor should be selected considering the legislation in force and the state of the art. Here follows the overall system architecture, where we have all the parts that make up the project. In the left, imagine that here we have the floor plan of university floor with a sensor in each room, where that is sent via LoRa to a gateway, and the server will receive data from the gateway via MQTT, which will be manipulated and presented on the RN Monitor platform. Here we have a block diagram of our prototype, in which we have an ESP32 microcontroller with a LoRa radio and temperature and humidity sensor, total volatile organic compounds and equivalent in the carbon dioxide equivalent. Finally, particulate material 2.5. The hardware used to grant the prototype was a LoRa Gateway 1 channel, ESP32, SGP30, VHT22, and SPS30. Here we have the development of the firmware, in which the SGP30 starts by obtaining the measurement of total volatile organic compounds and the carbon dioxide equivalent. Then you also get raw H2 and raw ethanol. Every 30 counts a baseline is returned, which serves to help calibrate the sensor. DH22 obtains humidity in percent and temperature in degrees Celsius. And finally, the SPS30 does a self-cleaning when started for the first time, and until the sensor is ready to measure the firmware, it is not started. Then start reading the data and measurement. Here we have the prototype with the sensors attached, and the dimensions are 95 millimeters length and 17 millimeters width, and 35 millimeters height, with all components assembled, and the total cost of the prototype is approximately 150 euros. Here are the preliminary results, in which they were obtained inside a room at home due to the pandemic situation experienced in the world. When the prototype is installed in the classroom, the values will be totally different. In obtaining results, some moments were taken into account, such as cleaning the garden, in which it makes a lot of dust and causes a significant increase in particulate material, and the cleaning of the room, and the number of people who were in the same formal, so taken into account. To conclude, a prototype for indoor air quality in the classroom has been designed and assembled, and the prototype collects the following indoor air quality parameters. The prototype was tested with success in the acquisition and the communication with the RN Monitor platform. Future work, activation of a ventilation grid, design a PCB, build box and the robust prototype, and finally validate the prototype in the classroom for a long time. Thank you for attention.
Hello everyone, my name is Pedro Santos and I'll be talking about NetButler, a voice-based edge cloud virtual assistant for home network management. As perhaps we have all experienced in our own home networks, sometimes we find poor wireless connectivity between our own personal device and the home gateway or router that is provided by the internet service provider. This home gateway or router is also often known as the customer premises equipment or CPE. Sometimes we may also need to activate a particular service, such as setting up a guest network for visitors. However, this task can be difficult for some users that don't know exactly how to carry them out. For such users, the only option is to call a support call center. However, this can become a frustrating experience. The customer may have to wait a long time before it gets to talk with a technician, and also the customer may be limited in his ability to explain the problem or need. As a consequence, we can expect the customer to create low satisfaction with the service. This is where NetButler enters. As we are probably all aware, virtual assistants have become an important element in our daily lives. They can be text-based, such as questionnaires or chatbots, or they can be voice-based, such as Microsoft Cortana, Amazon Alexa, and Google Assistant. NetButler aims to be such a voice-based virtual assistant, but with the particular aim of helping in the management of home gateways or routers by debugging possible issues or activating services. We expect that through this more streamlined experience, the customer will engage in higher satisfaction with the overall service. Let's talk about the structure of NetButler. NetButler is composed by three main building blocks: the voice and recognition synthesis engine, the virtual assistant manager, and the configuration agent at the customer premises equipment or CPE. The typical interaction workflow between the user and these three building blocks is as follows. First, the user will request an interaction with NetButler and provide a voice command. This voice command will be processed by the voice recognition and synthesis engine and will be transformed into a text input that will be forwarded to the virtual assistant manager. The virtual assistant manager will use this text input to identify the request by the user and to trigger the corresponding action at the home router or gateway. At the home gateway or router, the CPE, the configuration agent will carry out the corresponding debug or activation routine. Once it is over, the configuration agent at the CPE will provide a reply back to the virtual assistant manager that will use it to prepare a text reply to the user. This text reply is then forwarded to the voice recognition and synthesis engine that will synthesize this text as audio and provide it back to the user as system feedback. Let's now talk about the implementation of NetButler. Again, we find the three building blocks of NetButler: Underneath each one of them, we can find the technologies over which the corresponding building block was implemented. For example, for the voice recognition and synthesis engine, we used Alexa Voice Services and Alexa Skills Kit. For the Virtual Assistant Manager, we used the Java framework, and for the configuration agent at the CPE, we use Linux and Python networking commands. Let's focus our attention on the voice recognition and synthesis service. This service implements a text-to-speech and speech-to-text translation, and this is implemented by the Alexa Voice Services. You will notice that we use a third-party online service. This is because we found no suitable options for local operation. This is, to implement a TTS STT service on the CPE. As for why we used Amazon Alexa, we actually also tried with Google Assistant, but we found it to have some limitations. The use of a cloud-based voice recognition and synthesis service means that the architecture of NetButler spans over two domains, the home network domain on the left side and the cloud service domain on the right side. The typical workflow is that the user will use his smartphone to access the cloud-based voice recognition and synthesis service, in this case provided by Alexa Voice Services and Alexa Skills Kit. The Virtual Assistant Manager, implemented by the Java framework, will interact with the voice recognition and synthesis service to obtain the user input as text and to identify the corresponding routine that should be undertaken at the CPE. Through MQTT, the Java framework will inform the configuration agent at the CPE to carry out a given debug or service activation routine. Let's go through each one of these building blocks in a little bit more detail. The voice recognition and synthesis is composed actually by two services, the Alexa Voice Services and the Alexa Skills Kit. The Alexa Voice Services corresponds to the actual text-to-speech and speech-to-text engine. The Alexa Skills Kit allows us to define a skill, which we can consider as being an application-specific instance of Alexa Voice Services. This allows for Alexa Voice Services to be integrated or used by external applications that wish to have voice-based inputs or outputs. In this particular instance, we can consider the Alexa skill to be an Alexa instance that is fully dedicated to implementing NetButler. The typical workflow is that through the smartphone, the user input will be directed to the Alexa Voice Services, and in turn this will be forwarded to the standard Alexa services. However, if the user explicitly requests to use NetButler, the user input is then forwarded to the corresponding Alexa skill, which in turn will coordinate with the Java application in order to implement the NetButler application. There is an important advantage to this approach, is that the NetButler's Alexa skill can be instantiated in any Alexa-capable device. As for the Virtual Assistant Manager, it is implemented by the Java application, which has two main roles. The first one is to program the Alexa skill. Given a predefined set of use cases, we define the corresponding triggering utterances by the user, the corresponding procedures to be undertaken at the CPE, and the replies that the system should provide to the user. The table on the right side shows this correspondence. The second role of the Java application is to issue the commands to the configuration agent at the CPE so that the technical routines can be undertaken at the home device. The workflow is as follows. The Alexa skill will provide an user utterance in text to the Jovo application, which will use this user text input to identify the use case to be followed by the application. Correspondingly, it will start the procedure at the home device. Once the procedure is undertaken and carried out at the CPE, it will provide back some feedback data that will help the Jovo application to prepare a text reply to the user. Then this text reply is forwarded to the Alexa skill to be synthesized as audio. Finally, we arrive to the last building block, the configuration agent at the CPE. The tools implemented in the CPE are based on Linux and Python scripts that make use of networking tools. The configuration agent carries out the activation or deactivation of the functionalities at the CPE, as well as network diagnosis. As we mentioned earlier, the communication with the Virtual Assistant Manager is done through MQTT. Let's now see the use cases that are currently implemented in NetButler. These are the diagnostic of connectivity issues, the creation of a guest network, or direct requests for specific functionalities. Regarding the diagnosis of connectivity issues, we test for two possible causes of poor connectivity: poor signal quality at the user's device or an external bandwidth limitation. To trigger this diagnosis, the user just needs to issue a voice command such as "I'm having internet problems," "I'm having problems watching a video," "I can't access the internet." We test these two possible causes in sequence. First, we measure the signal strength of the connected devices, and if this is inferior to -80 dB, we will inform the user to approximate his device to the home gateway. If it is not, we'll continue the test and we'll carry out a speed and latency test of the internet connection to an external server. If we find the speed of the internet to be inferior to 25 megabits per second, we will inform the user that the problem is external and there's little that can be done locally. At the end of this procedure, NetButler always inquires the user if he wishes to reboot the home gateway. The second use case corresponds to the creation of a guest network. This creates a temporary wireless network, for example for visitors. Its traffic is separated from the regular wireless or cable LAN traffic. The guest network can be scheduled to start at a given time or to last for a given period. Finally, the user can ask for direct requests for particular functionalities. It can ask for an internet test speed, to restart the router, or to count the number of connected devices. On the left side of the table, we find some examples of user commands such as run a speed test, reboot, or how many devices are connected, and the corresponding replies by NetButler. Finally, we will describe the evaluation that we perform of the NetButler system. The evaluation consisted of carrying out 3 use case scenarios by 8 test users. We could only gather 8 test users due to the ongoing COVID pandemic crisis. We measured the time until the problem was resolved or the functionality requested by the user was activated. At the end of the test, we also posed a questionnaire to the users to assess their user experience. The tests were as follows: create a guest network, either turning it on or off; diagnosis of connectivity issues, namely those caused by poor signal strength at the user's device; and the third one is the diagnosis also of connectivity issues, but this time due to an external bandwidth limitation. The average time taken by the 8 users to turn on the guest network was around 14 seconds, and to turn off the guest network around 13 seconds. To identify the poor signal strength at the user's device as the cause of a problem, it took around, in average, 31 seconds. As for identifying an external bandwidth limitation, the users in the system took around 68 seconds in average. You should be aware that the test 3 contains also in itself the time taken to carry out test 2, which happens in sequence before the test of an external bandwidth limitation. Regarding the post-test questionnaire, we asked the users to classify from 1 to 5, with 1 being the least positive and 5 the most positive, their opinion on a series of aspects regarding their experience with NetButler. We asked them about what they think about the clarity and objectivity of the assistant's replies, as well the technical depth of those replies. We also asked them if they considered the solutions proposed by the system to be suited to the problem or need that they had, and whether they considered the problem was solved in a reasonable time. Finally, we also asked them to evaluate their overall experience with the system and whether they considered virtual assistants to be a potential good solution in the future to support the management of home networks. In this last question, the test users were unanimous in providing a grade 5 grade to this question. And as we conclude this presentation, we presented NetButler, a voice-based virtual assistant to support the management of home networks. The evaluation by test users shows satisfactory performance in addressing problems or needs in domestic gateways or routers. All things considered, we consider the system to be competitive against the current solutions, namely customer support phone line. In future work, we expect to expand NetButler with additional use cases and more dialogue options, adapt NetButler to Portuguese or other languages as it currently only operates in English, collect information about the most common problems, and extend NetButler for offline operation, becoming independent of a connection to the cloud. Thank you for listening. Let me also invite you to watch a short video of NetButler in operation.
Alexa, open Network Manager.
Hi, what can I do to help you?
Create a guest Wi-Fi.
The guest Wi-Fi will be available in a few seconds.
Hello everyone, my name is Tadeu Brito, and today I will present the work named Environment Monitoring Modules with Fire Detection Capability based on IoT Methodology. Here you can see the path that we will take during the presentation. Starting by motivation, then I will talk about the problem and the main objective, the implementation of our system. Then I will talk about the sensor models and his assembly. At the end of the presentation, I will summarize the results, conclusions, and future works. As we well know, Portugal suffers from forest fires every year. This causes a lot of damage to the population and the environment. Over the years, several fires places have been recorded from south and north. Even surveillance systems are not sufficient to monitor our regions. And many times, the delay in alerting forest fires can affect the decision-making of firefighters. To avoid this, the right way would be to develop a system capable of monitoring these areas with sensors. This system should be of low cost, analyze the data, inform the authorities, and collaborate with the existing surveillance systems that have been done in Portugal. Here you can see an illustration that summarizes the purpose of this project. A system that can gather data from a sensor network to determine forest ignitions. We can divide the entire project into 8 sectors. I don't have much time to explain the whole project, so that I will focus only on number 2. As you can see, we intend to spread many sensors along the forest. The development of this device needs to consider a series of restrictions, such as size, battery autonomy, low cost, and support several sensors types. The central element of the model is the AT-MEGA328P. It is low cost, versatile, can be powered between 2.7 to 5.5 volts, and also it is easy firmware update using RX and TX pins. This battery supplies the entire circuits. However, it is necessary to maintain the voltage at 3.3 volts and to measurement the remaining battery charge. To measurement the remaining battery charge, an analog port of microcontrollers is dedicated. The sensor modules. It's possible to insert sensor modules with SPI and I2C interface. For example, we can insert the DHT11 to get humidity and temperature, or use several sensors via analog or digital ports. Thinking about low consumption and cost, the LoRa communication was chosen for this project. The RF95 device received from the microcontroller the data and sent to the LoRa gateway. The interval is 60 seconds. Here you can see a prototype assembly. Note that some components were chosen to be on the board edges. Now you can see the final prototype assembly. And then we can make some tests about this. We can make some tests with these modules. Concerning this, 9 modules were spread around the IPB in 5 points. The 5 fixation points were chosen according to the soil type and tree. In this sense, the performed by modules 1 and 2 are joined close to the builds, near to here. Module 3 and 4 are attached to tree trunks in a small orchard, and or here, and module 5 and 6 are positioned to medium-sized 3 around in Fervenza River that crosses the campus. Here. On the other hand, modulus 7 and 8 were fixed off campus. Here. In a reserve with a high tree cover density level. And the last module 9 is set on a tree planted in a garden. Here. Some examples you can see some examples here. In the first one is the sensor module 1, then the sensor module 5, then the sensor module 9. All data were collected together, respecting the 60 seconds interval. At this point were two modules, and this graph indicates. Okay. In this point 1 are two modules, and this graph indicates the values collected from the first point. Similar to the previous test, this point also has two modules. Module 3 and 4 are attached to the tree trunks in a small orchard. The same for point 3 that represents the data from modules 5 and 6 near to the river. And point 4 with modules 7 and 8 fixed in a small woodland. The last one is the module 9, placed in a garden, limit point 5. The flame sensor chosen is affected by sunlight, so the graph shows the sensor data from modules 7 and 8. This point is a region with a dense covered trees, that is, it has some shadows. This allows the sensor to collect the data. You can see here when the signal comes down and goes up again in this time. Some conclusion, such as this work generated a prototype with capability to acquire and transmit Wi-Fi ignition through LoRa web. This approach can be used to improve decision by firefighters and civil protection with more details and real-time information. As a future work, a new firmware will be developed to decrease the transmission rate, while ensuring rapid fire detection and a battery consumption reduction. Furthermore, different flame sensors will be evaluated. I would say thank you to Promob by Fundação La Caixa, and say thank you to you. If you have questions, please feel free to ask me.